And how do we do that? By using the label data sets, right? Supervised machine learning, they learn to map the inputs to outputs. So based on the examples which we could have. So basically, this approach is widely used in the applications when we talk about image processing or image recognition, when we talk about spam email detection, as well as predicting the numerical values like house prices and those things. Those are the places where we use the supervised machine learning quite a lot. And then when we talk about the supervised machine learning, when we know the input or we give the details of the input and then we also say the desired output, then comes where we do not do that. And that is being called as an unsupervised machine learning. So where what we do is that here the data is unlabeled, absolutely. So the model tries to uncover the hidden patterns of the structure within the data without predefined outcome. So basically, if you will think about the unsupervised machine learning, the common technique generally include here is that one of the very famous one is clustering. So what this do is that this group similar data points together, dimensional reduction. So that actually simplifies your data set with retaining important features. And generally for when we talk about unsupervised machine learning, the applications always include somewhere like customer segmentation or definitely anomaly detection and data comparison. So these are the kind of examples of unsupervised machine learning. And then comes with the supervised and unsupervised, which is the another one, which is the reinforcement learning. This is based on the idea of an agent interacting with the environment, right? So the agent takes decision and gives feedback in the form of rewards or in the form of penalties and learn over the time which actually yield the best outcome. This approach underpins somewhere like self-driving cars, robotic systems like AlphaGo, those kind of things. So we will look into more details onto that in the coming slides. But if you kind of try to understand this together, you can see that together this paradigm from the back, this is actually the backbone of the machine learning method. And they can also even be combined in hybrid approaches. Sometimes you will see that there are some methods where we are actually using these two together, or some way supervised or unsupervised. So it could actually be also used together depending on the case we are discussing about, right? So now we will try to take each of these cases. We will try to understand the detail of it. We will see also a little bit of the examples, case study, and how further infrastructure is possibly work. Definitely, we start with one of the most widely used approach in machine learning, which is being called as a supervised machine learning, right? So we will see that most of this machine learning algorithm, they create a prediction model. So given some output, these models produce some kind of, given some input, these models actually produce some kind of output. So if the output is a discrete value, then it's a classification task. And if it's a continuous value, then it becomes a regression task. So both of these tasks actually come under supervised learning. Okay. And what we generally do here, we are learning from the label data. So supervised learning means that the algorithm which we generally use in the supervised learning, the algorithms are actually learning or they learn from the label example. So we provide input features, if you can call them some way like X here, right? And then corresponding to the X, you also give some targeted levels or the output, which is being we call as an Y. So you can see that the algorithm then learns to map X to Y so that the prediction of the level of new unseen data that points accurately. So that's how generally we do. And the goal of this kind of supervised learning is that to train the model which can generalize very well. In other words, you can say that it not only fits the training data but also performs well on the unseen data. You cannot see that, right? So depending on the algorithm, the mathematical model may take different kind of forms. For example, if you think about the straight line, a straight line in a linear regression, or you can think about some kind of complex decision boundary in the neural network. So those are the mathematical representations we generally use when we talk about this kind of supervised learning. And if you think about the examples, there are two classic examples. Another very, very commonly used one as a linear regression. Basically, it helps you to predict the values, logistic regression, which classifies the data into categories, whether it's yes, no, some thing like 0, 1, so those kind of examples. So basically, you will see that essentially when we talk about the supervised learning, that is about teaching a model with known examples so it can make reliable prediction of the unknown data. And now there is a very nice diagram of the supervised learning with more details. So we start here with the data set which we call as a D, and which considers the endpoints of data. So now if we try to think about this, what could be the goal of the supervised learning? If you think about the objective of it, so what is the objective is for this kind of thing? Yeah. Yeah, absolutely. So basically, we do it in a T process. So if we will look into this particular diagram here, first what we do is that we try to kind of train the data. That means we use it to teach the model, right? And then what we do is that we do it the validation set. So in that case, what we do is that we use the tune model parameter and prevent outfitting. So that, and after that, the final set is that we use the test data. So completely unseen data that is being used to evaluate how well the model generalized for the new case of example, right? So basically, there are three steps to do that. Which we also call as the data splitting method. So first is training data, second is the validation state, and third is the test data. So now if you look into this particular diagram here, you can see that in the process identified here. So we are starting with the data set and then we feed into the training, validation and test this three one, right? And once these three are done, that means the model affects this one is trained using the training data set, right? So then tune using the validation data and then finally what we do is that we do the evaluation. So once the evaluation data is done, then we try to estimate the real world performance. So basically, this is the diagram of the supervised learning, which is generalized diagram, I would say. It can be complicated depending on the case. But in short, what we could possibly say is that supervised learning is about learning a function from label examples and then rigorously testing it on the unseen data to understand or to kind of ensure that it generalizes well. And if you will look into the supervised learning compared to the unsupervised or enforcement learning, you will see the process is quite simple. But if you talk about more realistic cases, you will see that unsupervised learning is more realistic compared to the supervised learning when we talk about the real life scenarios. Okay, we will see those things soon. So now before getting into the unsupervised learning, so we will try to quickly look into the types of the supervised learning when we talk about. So classification algorithms are used. So I have tried to divide it into two main sections. One is the classification one, right? And one is the regression one. So basically, when we talk about the classification algorithm, they are used when the output variable is categorical, right? For example, if you think about predicting whether an email is spam or not spam, or whether a patient has a disease or not, those are actually come under the classification method. So in the classification method also there are various ways to do that depending on what you need. So classification tree or the random forest, they are basically tree-based methods, and what they do is that they try to split the data into different kind of classes. Okay, and then comes another one which is the support vector machine, which is also being quite used a lot. It's like SVMs. They try to help you to find out the optimal boundaries between the classes. And then artificial neural network is also one of the important one, and they help us to model the complex nonlinear decision boundaries. And then there are several others such as naive Bayes or k nearest neighbor, KNN, that help is to point based or its closest neighborhoods. So that's what the k nearest does. And then there are another one which is the logistic regression, which despite the name it mainly used for the binary classification. And then another one is the assemble method, which combines multiple models to improve the accuracy. But if you try to look into all of these classification methods, you can see they are mainly used or they are mainly applicable when the output variable is very, very categorical, right? So now if you move into the next one, which is the regression model, a regression algorithm are used when the output variable is a continuous process, okay? For example, predicting the house prices or stock market, temperature, those comes under the regression method. So regression method has also different types. One, linear regression is one of the very, very famous one. We always, day-to-day basis, we use that. It's the simplest model. It's basically nothing but fitting a straight line to the data, right? That's what we generally do. And then there are generalized linear models. They extend this is basically extension of this linear regression model for the non-normal distribution. When we do not have normal distribution, that's the time when we use the generalized linear model. And then definitely there are decision trees, there are Bayesian networks, and they basically mainly use model relationship between input features and continuous outputs, right? And then there are neural networks as well as Gaussian process regression. They capture the complex and nonlinear relationships. So when you don't have a linear data, when you don't your data are not behaving as a linear way, then generally we use the neural network or use the Gaussian process regression. Then also comes another important one, which is the support vector regression. We call it as an SVM. This is also adapted from the continuous output. Basically, your output has to be continuous. That's the one of the important one on the regression. Where for the classification, the output was categorical. So that's the main difference between classification and regression. And then the last one is definitely the assemble method. I think they combine the multiple types of regression model for better prediction. So that can be linear, that can be non-linear, depending on the particular case. So basically, if you will try to look into these two types of cases, you can see that as I said, classification is more categorical outputs, whereas this all are talking about more continuous outputs. Most of the supervised algorithms, most of the cases you will see, we will try to consider any one of this. You will see that most of these actually fall under all these 20 cases, right? I mean 10 each. So most of these cases will either fall under classification of any one of this or regression. Definitely there could be different kind of artificial neural network or neural network, but it will fall under any one of this. So that's generally the supervised learning mainly works. And then we'll try to look into few of those supervised learning, which is going to be important for us. So one of the very, very simplest one, I think most of us know, is that the linear regression, right? So they are mainly used to model the relationship between one or more input variable like x and a continuous target variable y. So your input features has been said as x, your continuous target variable has been said as y, right? So that finds the best fitting straight line. Basically for hyperplane or higher dimension, that explains how the input feature influences the output, okay? And with the mathematical, if you will try to kind of use the mathematical expression, it generally looks like this, where the y is mainly the predicted value and beta 0 to beta 1, beta 2, they are basically the coefficient which is to be learned through the process. And as we know that x1, x2 and x3 to the power, because we are taking n parameters, right? They are basically the input parameters. So we can express something like that. What is the main objective of this particular kind of model? The main objective here is to minimize the difference between the predicted values and the actual values, right? Also it is been called as an error or residual. So we do this by adjusting these beta values or the coefficient, and then the model fits the best. So that's what we generally do in this kind of cases. And how we kind of achieve that? This optimization is usually done by ordinary least square, if you have heard about it. And what we do in the ordinary least square, we try to minimize the sum of the square errors, right? And we can also kind of do in another way, which is been called as a gradient descent. So there are several ways we can do that, but the aim is that we kind of play around with this beta value, right? And this is your y, which is the expected output, and this is your x, which is your input feature. So that's what we generally do by playing around with this coefficient, okay? So in a short way, you can say that this kind of models actually provide you a simple yet very powerful way to make the prediction for very continuous output by fitting a linear relationship between the input parameter x and the output parameter y. So then with the logistic regression, as I said, that this is also one of the very common algorithm for classification. So if you will look into the linear regression and try to compare with the logistic regression, you will see that while linear regression is for predicting the continuous values, but for this logistic regression, what we do is that we try to use it for binary classification problem. Cases where the targeted variable y can have two possible outcomes. That's the difference between the linear regression, such as spam, not spam, right, or disease versus no disease. So target variable y can have, so this is your target variable y, that can have two possible cases, okay. And how it could generally work? So instead of predicting a number directly, this logistic regression, what they do is that they predict the possibility of an input belonging to a class, rather than saying, okay, fine, this actually belongs to Y, or belongs to not under Y. This will tell you the possibility of belonging to the Y. So it does it using the logistic function, or we also some way call it as a sigmoid function, which maps any real number to a value between 0 and 1. Okay. And the mathematical expression, if you will try to write it down, it looks something like this, okay, where the P or this function actually represents the possibility of the positive class X, and X is, as we know, the input feature, and then Z is the linear combination of the input feature and the corresponding coefficient. So the mathematical expression some way, so we will try to do some of the tutorials tomorrow to understand some of these cases, but now we are not getting into more mathematical expression, but try to understand how it could possibly look like, okay. So X represents, as I said, the input features, the Z is the linear combination of the input features and their coefficient, similar to some way like the linear regression, okay. So the models, what we do is that we try to also learn from the coefficient. And how do we do that? The models coefficient are learned by maximizing how likely the observed data is under the model, okay. So typically using the maximum likelihood estimation or the gradient descent, these are the two types of method we use to optimize the fit. So basically, if you will try to talk about the logistic regression, you will see that they generally gives you a probability of class of membership, which can be converted into a class level 0 or 1 by using this threshold, like usually like maybe 0.5 or something like that. So what is the comparison, or what is the difference between linear regression and logistic regression? If you think about your output Y, sorry, yeah. Yes. Yes, right. Right?
How do you deal with the vanishing of gradients when you deal with using the gradient descent? There is chances of vanishing. So
Yeah.
how do you deal with that?
Sorry, I couldn't hear you. Can you say that?
In this method, it
Yeah.
is difficult to use the gradient descent.
Yes.
When it
So there are two methods. We can use gradient descent. We can also use maximum likelihood one. So can you?
the extension function is sigmoid,
Yes.
and the sigmoid will split the any type of data between 0 to 1.
Yes.
Whenever the neural network is a large neural network,
We're not talking about that neural network here. Yeah. Yeah.
there is also the estimating in terms of some regression.
Yes.
There is also some multiplication factor games.
Yeah, that should be possible. Yeah. Yeah.
So when the sigmoid is split the data between 0 to 1.
Yeah.
So, and when the value is near the 0,
Yeah.
most probably most of the
Yeah. Yeah.
then
Yeah.
if the number of factors is multiplied,
Yes.
the overall result will be more closer to the 0.
So that's what basically the logistic regression does compared to the linear one. That it is not going to tell you, fine, okay, it's 0 or it's 1, right? It will tell you like two possibilities, that it can be under 0 to 1, right? And then according to the coefficient you take, then you get a value that, okay, it could be 0.5 or 0.6, but it could be near to 0 or it could be near to 1. It is not going to tell you, okay, it's going to be 1. That's the main difference if you look into that. So it's possibly going to give you the probability rather than giving you the exact number. So that's the main difference in this, right? So this is a very important one, and we do quite use the ANN one. This is one of the very powerful supervised learning, I would also say, and we do use it quite a lot in the SHM techniques. You see that. So when we talk about artificial neural network, they are mainly computer models. They're inspired by the way human brain works. Okay. They consist of the interconnected neurons that can learn the pattern in data and perform tasks like classification and prediction, right? So now if you will try to look into this particular image here, there is a single neuron receives a multiple inputs, which is x0, x1, x2. I mean, you can go till xn, let's say that. And each of these multiplied by the weight of w0, right? And then you can go to till wn or wherever it goes. These are the summed up often with a bias term. But if you will try to look into this one, this is a quite simpler way of expressing how does it work. It generally have a three sections, okay. One is the input layer, one is the hidden layer, and one is the output layer. So artificial neural network is made up of these three particular sections, okay. So what is the first one? This is where the features are fed. That means age, gender, coordinates, those are the things, right? And what is your hidden layer? The hidden layer is the intermediate layer where the model learns the complex pattern by combining the input in a non-linear way. That's the main thing where it actually works. So you give this input layer and then here it is actually learning about this input layer, and that's been called as a hidden layer. And then definitely when we giving our input, then we definitely expect the output. So this is the final prediction or the classification. That means it can be high versus low risk of that thing. So basically, if you talk about the ANN, this has been concerned about 3 steps which is being shown here. So the network actually learns by adjusting the, if you will look into this one. So what generally the ANN does is that they try to understand by looking into adjusting the weight, and that's some way you can look into the, comes under the input layer. So now if you will try to look into the first picture and try to combine it with the second one, so where does actually X0 and W0 falls? Does it fall under input or hidden layer?
Actually, that is an input, like age is something as or same inputs. And at it, when it multiplies, it goes to the hidden layer. And at hidden layer, we apply the activation function.
So what is Y0? Why Y0?
Y0 is output.
And what is W0?
Wait.
Where does W0 fall? Does W0 fall under the input
Arrow.
layer or hidden layer?
It is an arrow. It is a weight.
So it does not fall under hidden layer, neither it falls under the input layer. Perfect. Yeah, that's the thing you have to see here. So now when you look into that, this X0 to Xn is basically your input layer, okay? And your hidden layer is that where your structure or your model is actually learning from the input layer. So basically this is the process where it is going on, and this arrow which you can see in there, that means going from input layer to the hidden layer, that's where the W0 works. So basically the network learns by adjusting the weight during the training to minimize the difference between the predicted output and actual output, right? So typically using this algorithm like back propagation with gradient descent and those kind of cases we do use that. But in essence, if you will try to look into this ANN here, they take inspiration from, as I said, biological neurons, but have implemented in softwares to solve the complex texts as an image recognition. That's very something in SHM we do quite use a lot. And then natural language processing, medical risk prediction. So those are the places we use this kind of supervised learning. But this is one of the very powerful supervised learning if you look into the whole details.
In this case,
Yeah.
you mention only about the weight, not about the biases. Suppose if the input is like 0,
Yeah.
then maybe that whole neural network will be collapsed.
Yeah, that's why it's very, very important that what is the input layer you are actually giving, or what is the input information you are giving, right? And then when you are giving the input information, then how you are making learn your model. That means that the value of the W0, what are those things you are giving into that?
Biases is not added in this cases.
No.
Why?
Because we are not concerned about that. So when you are talking about this ANN cases here, 2 things is very, very important. The first is that your information of X, everywhere it is very, very important. But if you look into this particular arrow, that means that what information you are feeding from this place to this one. That means when it is going to learn the details before that with the input layer, what are the information you are giving. So your W value is also somewhat important, and there is that if you kind of take some kind of bias that okay fine, you may not be uncertain about those things, that's the place you can have wrong output layer.
Because it is not a necessity to always only one
No,
area.
absolutely. So you can, it's always not important that you need to give W0. Depends on the cases. You may not need to give the W0. Sometimes it could possibly happen that you give the value of ages, right? Or X0 to Xn, and you don't need to give the value of W0. That depends on the case to case, that where you need to put the value of W0, and that depends on your model. So not everywhere you need to put the value of W0, but basically it could possibly happen that your X0 may have the information of W0. It could possibly happen that you don't need to kind of give the value of W0, that it itself, the X0 will have all the information to kind of get into the, train the model. Get it what I'm saying? Yeah. So then and then there is another, and the another very nice way of understanding how does it actually work. That means the learning goals or the learning objective. So the objective, as I said, of ANN is to adjust its weight so that its output matches the desired output, as I said, right? And how the learning process mainly works. So you can see that, as we know that the correct output for each of the input is important. So what ANN does is that ANN takes the input, okay, produces an output and compares it with the known result, right? So if the input is correct, the weight stays similar. If you go back here and try to again look into this and then come back to this particular case and then you think about this particular case, okay? So if the input is correct, what happens? The weight stays similar. Understand? And if the output is wrong, then what happens? Right? If the output will wrong, then the network calculates the error and go back and recalculate the weight and update the weight, right? And this process is repeated many times, iterations happen many times until the model predictions are sufficiently accurate. Okay, so that's why generally the ANN works. So now if you try to kind of look into the diagram here, you can see that diagram at the bottom shows this circle, this one, right? So the input goes into the neural network, then the output is compared to the known result, right? And then reference, that means the error is being used to adjust the weight. Right? And that's way always it works. So basically the trial and error process, and this is usually in the basis of the backbone, or we can also use the gradient descent in neural network. That's how it generally works. And then there are several types of ANNs also. There are many types of neural network, but one of the most widely used one, anybody has any idea that are there any kind of varieties of ANN? Have you ever heard about it? Yes. How have you heard about multi-layer perception? Yes. Yes, yes, right. Yeah, right. Anyone else have any idea about the different varieties of ANN? Yeah. Yes, absolutely. So among all of this, you will see that as you said, that the multi-layer perception or MLP we do quite a lot in the SHM cases, right? Because it has an input layer, one or more hidden layer, and the output layer. So it's quite simple, not quite complicated, right? So and then in short, you can see that basically this is mainly talking about how the ANN works. So you understood how the ANN works. If the input is correct, the weight stays similar. If the input is not correct, it will go back, recheck it, recorrect your weight, and then the trial and error will go unless you will get a Y which is expected, right? Is it clear to everybody? So then there are several other kinds of also supervised learning algorithm, and one of the very important one is the decision tree. So this in the decision tree, what happens is that decision tree split the features of space into region based on simple rules, right? And at each of the split, the data is partitioned so that similar outcomes are grouped together, and predictions are then kind of being calculated or being made based on the majority class in each of those regions, right? So they are each easy to interpret and they are very easy to visualize as well, but they can overfit without the proper ruling. So you have to be really careful when you use the decision tree. Whereas another important one is the support vector machines, which is also being called as an SVM. So SVMs are designed to find out the best decision boundary between the different classes of maximizing the margin, right? So the distance between the boundary and the nearest data point from each of this class. Okay. So this makes a very powerful for the high dimensional data and for cases where the clear separation exists, right? And then there are another one which is name based, and then the another important one is also the k nearest neighbor, which is also being called as an KNN. KNN is a non-parametric algorithm. It's very realistic. Many of the complicated cases we do use it. It classifies a data point based on its proximity to the other level points, right? In most of this, it is nearest to the neighbor, belong to a certain class. It is classified into the class. It's simple, it's intuitive, it works well with the recommendation systems, and it's also very good with the image recognition. So we quite use a lot on the image basis techniques as well. But it can be computationally expensive. So that's one of the issues with this k nearest neighbor, because as the data set grows, your calculation becomes complicated, right? So if you will look into these algorithms, you can see that these algorithms will actually provide a different approaches to supervised learning, and each of these has their own strength, each of these has their own weakness, depending on the data and the problem, right? And then let's try to take a case of this supervised learning. So here the problem is that we are dealing with this civil infrastructure. You can think about bridge, tunnel or dams where safety and the maintenance are very critical, right? So how does it work? So let's try to have a quick look into that. So maybe let's think about we are taking some kind of drones or other sensors. They collect the image of this infrastructure. This can be any kind of infrastructure, okay? Civil infrastructure definitely. And then these images are then labeled by experts to indicate whether there are some kind of cracks, defects are present or not. So once you collect the data, what we generally do after that?
Data pre-processing something like that, like feature extension or something.
And how do we do that?
Depends upon the either previous experiences or either the different variety of the feature expression.
So if you try to look into this particular diagram here, right, this is the process generally we say as a supervised learning. So now if you look into the data again, look into the figure again, and now let's go back to the case here. So now what is the process we do for the data preparation? Your data is collected. So what are the 3 steps we are gonna do here?
Divide it to training and verification.
Yeah, right. The three tests we need to do. First, we need to train the data, because you just cannot collect and analyze the data. You have to train the data. That means that will help the model to recognize the patterns, right? And then we will do the validation set, and how we will do that, to fine tune the model and prevent the outfitting. And then the test data will evaluate how well the model performs for the unseen data, right? These are the 3 things we will do. So the data collection is done, data preparation is done. So now what is the next step? Yes, the model training, right? That means the supervised model. You can say any kind of, like maybe let's take CNN, right? And that is being trained on the data set to classify each of the image as either there is some crack, there is no crack, and that's the general process we do for this kind of supervised learning. And this is the method depending on whatever supervised learning you use it, but this is the generalized method we do use it. And then once there is crack, no crack, then the final one is the output and maintenance decision, right? That's the final one. So basically the trained model output whether there is a crack detected or not, and the information is then fed into the maintenance system, right? And that will prioritize inspections or repair based on the detected condition. Whether there is a crack, what is the intensity of the crack, whether that needs immediate maintenance. So that decisions are going to be taken care of. So basically there are mainly 4 steps of this. First is you are collecting the data, you are preparing the data, then you are training the data, and then you are taking the output and maintenance, right? These are the 4 steps we generally always use when we try to do that supervised learning. Not only for the SHM, for mainly all of the cases you will see that. And when you see this case study, you can also understand that how supervised learning can automate structure inspection, reduce the manual effort, and improve the safety and longevity as well. So that's the one of the important case study. So now let's try to move into the unsupervised learning. So the unsupervised learning is that another second branch of the machine learning. So basically, unlike supervised learning, unsupervised learning deals with the unlabeled data, right? So that means the algorithm does not know the correct output or categories beforehand, and there are no target levels or class information being provided into the set. So how generally it works? So the algorithm tries to find the pattern, structures or relationship within the raw data by itself. So it clusters similar points and detects anomalies or reduces dimensionality, right? So in supervised learning, we tell that, so if you think about the supervised learning and the unsupervised learning, in the supervised learning, what we say that we have the data. If we identify this creature or the animal as a dog, this is how it could get the details, right? And what you do using your supervised learning model, you train the X by giving the information of those so that you get the Y which looks like dog, right? Whereas what unsupervised learning is does that you have a dog details, you have a cat details. So they don't understand, okay fine, this is something dogs look like. They will differentiate those two. And they will say that this information looks exactly in this pattern and this information looks exactly in this pattern. And then you understand, okay fine, this is looks like a dog pattern and this is some another kind of animal, right? During the training. So that's what generally in unsupervised learning we do. We don't provide any levels. The algorithm groups similar things together purely based on their features, right? And then we interpret those groups afterward. So you can see that basically if you talk about the real life scenario, unsupervised learning is actually very kind of used a lot, but it's also complicated because someday you have to also understand the data or the output you get, and the prediction level is little bit critical compared to the supervised learning, right? So as you see that, that's what I have tried to kind of show you using this diagram. The diagram shows how a set of unlabeled animal image goes through the algorithm and then process it further, interpret the data and the output clusters. So one group of things are being called as dogs and another one is cats without being told that in advance which one is what, right? So in short, actually this kind of unsupervised learning that will help you to uncover the hidden patterns in the data and is widely used for tasks such as clustering, market segmentation, animal detection, dimension reduction. So those are the examples where we do use the unsupervised learning a lot. And then as usual, there are broad types of unsupervised learning, right? One of the very important and most used one is the clustering, okay? So what is clustering? Clustering is about grouping similar data together. Like you are getting a data of dog. So what you generally do is that you put it all together and try to get an output and a prediction. And that's what generally the clustering works. So objects that share the same features end up in the same cluster, while the dissimilar objects are placed in the other cluster. This is very helpful for segmenting the customers, grouping the genes and organizing the large image data sets. Algorithm like k-means, hierarchical clustering or DB scan, they are very popular example of clustering. And then the another one is the association. So association is basically a learning focus which is on discovering the relationship between the variables in large data sets, okay? It is often used in market basket analysis, or for example, people who buy bread can also end up buying the butter, right? That's why generally this work, that how it is associated with each other rather than coming under the same group. And the algorithm actually identifies these rules without any levels. Absolutely, we are not putting any details. These are all unlabeled data, helping to improve the marketing strategy. So we know that, okay, fine, whoever comes to buy the bread, they always keep buying the jam or butter, right? And that's the thing we kind of understand, and that always helps you to understand the marketing strategies. So common example is, as I said, that the bread thing. So there are a lot of other popular algorithms as well, except that, which is the k nearest neighbor, which is k-mean. There are k-mean clustering, and then there are animal detection, neural network for feature extraction, principal component analysis, then singular value decomposition. So there are several kind of rules and clustering methods we generally use in unsupervised learning. So basically, while clustering focuses on grouping the similar data, you can see that association type of unsupervised learning actually focuses on finding the hidden relationship. Together they kind of form a backbone of the unsupervised learning. So it's not necessary that every time you will end up using one of these. It can possibly happen you may end up using both of these together, right, depending on the particular circumstance. So that's how generally it could possibly work. And then there is a very another most popular one is also like the k-means clustering. This is also being used quite a lot. And k-mean clustering is basically partitioning the data into the k groups or maybe the clusters. The goal is to minimize the sum of the square distances between the each of these data points and is assigned as a cluster or centroid, okay? And how generally it works, it's also having 3 to 4 steps. First one is the initialization. So we start selecting the k centroid, either randomly we do that or by providing some input here. So and then the next step is that assignment the steps. So each of the data is then assigned to its nearest centroid. So you can see that this red one is being called as a centroid. Each of these, so there are processes to do that. So first, and this is also a trial and error process as well. So each data point is then assigned to the nearest centroid based on the distance from it, okay? And then for each of these cluster, a new centroid is calculated, and as the mean of the all data points are assigned to it. And then we repeat the process similarly, right? And why we take the mean? Because the mean in k-mean refers to the averaging the data points in cluster to find out a new centroid during the update stage, right? So the characteristics here that, or the k-means works best when the clusters are roughly spherical and similar in size. So if it's like all of these points some way similar to each other rather than one is very big and another one is they have to be a little bit similar in size. So if you will try to look into this diagram here, the blue dots they represent the data point and the red crosses the cluster centroids. So the algorithm tries to arrange in such a way so each of these clusters is compact as compact as possible and separated from each other, okay? So in short, you can see that this K-means is a simple but very powerful way to discover the natural grouping in the unlabeled data. Now let's try to see how actually the process works. So first what happens is that iteration process, right? With each of these pass or each of the iteration, every data point, that means which is being called as the blue one, is assigned to the nearest cluster center base, right? On the current position of the center. So these ones are the centroids here and the blue ones are your data points, right? So once that is being done, then the updating the cluster center. So how that is done? Once all points are being assigned, the algorithm then recalculates the cluster again. This means that taking the average of all the points in each of the cluster to define a new centroid, right? And the rate process, now we will try to look into this one. So the rate process on the diagram, they represent the centroid as I said. And then again the same process will be done until the convergence is being done. So until you kind of fit into in some process where you can see that all of these groups are little separate than each other. The centroids are lying inside their points. So until you reach somewhere there where the algorithm keeps repeating these two steps, which is the assignment and update. Okay. So until the centroids no longer move significantly. So your points will no longer move significantly. You will keep repeating that. So in short, you can say that K-means is an iterative process, right? That refines the cluster step by step until it finds the most stable and compact grouping of the data. Okay. And then there is another important one, which is the DB scan. So that is being called as a density-based spatial clustering of application with noise. And why it is important? So unlike K-means, where we assume that the clusters are spherical, right? And predefines the number of clusters and the size of cluster, they look somewhere similar. They look, they will look like the spherical. So what DB scan does is that DB scan groups point based on the density. So it defines the clusters as region of high density separated by the regions low density and can also be identify outlines or noises. Okay. So if there are no noises and you want to just group your data, find your centroid, then I think definitely K-mean clustering is safe. But we assume that for the K-mean clustering, the data has to be similar. Density has to be similar. The sizes of it has to be somewhere similar, and then it has to be like somewhere spherical, the data set. Okay. Whereas when the non-linearity comes or when the uncertainties come into your data, then definitely density-based spatial clustering is very good. When you have noise in your data, it can very nicely identify that. And DBs can actually automatically find the cluster of arbitrary shapes. So if you have different kind of shapes, different kind of sizes of your data, so without defining the number of clusters, it can actually naturally detect the noise. That's also one of the advantages compared to the any other cluster. So that's don't belong to any cluster. So if you have some kind of noise, that will automatically separate that. Okay, so that's the actually good one. And the main difference with the K-mean is that this does not only rely on centered or average like the K-mean. So it instead it relies purely on the point density. Okay. This makes it very special, good for irregularity. That means if you have something on square, if you have something on, some other kind of shapes also your data points, it can immediately make a cluster. It can immediately kind of define it. And especially when you don't know the number of clusters in advance. So that's the also time when DB scan is being used a lot. So DB scan is actually a robust algorithm for clustering of real life cases. In the real life, it's always, you definitely not find a spherical data, definitely not find the data which have the same density, or you will definitely find a lot of noises most of the cases. So DB scan is very, very realistic, and where the clusters are not nice, neat, and may contain noise, which is the more realistic case. That's the time when we kind of use the DB scan a lot. So now again, there is another kind of case study where let's try to look into the unsupervised learning, the method how it could possibly work. So here, we often kind of collect the large amount of sensors or image data from the structures, and let's consider breed, building, whatever you want to consider. But we don't always have the levels telling which data point corresponding to the which structure state, right? So what we first do is that, first on the left hand side, you have the data, right? So you will start with the collecting data from the structure. This could be vibration signal, this could be your strain readings, acoustic emission, or even images, right? The key is that this data reflect the condition of the structure and they are not labeled. Okay? So once you have the data, so what we do after that? Sorry? call the process? Clustering?
Can be clustering. It is basically a method of reinforcement learning where the
If you think about, you have the data, right? You do not know what is the level, what exactly does it mean. So what is the basic thing you will do? You will try to separate the data, like what looks similar will come under same cluster, what does not look similar will go to the different cluster, isn't it? Right? And that's what we do here. We kind of, once you have the data, because we don't have any kind of knowledge, we are not feeding any kind of knowledge in the data. So once we have the data, we kind of separate it, that what looks similar, what does not look similar, and how we do that? We're using the clustering method, right? So in the middle, we use a clustering algorithm. Anything, you can use k-means, you can use TP scan, depending on whatever is appropriate for your case. That means that will help you to group the data based on the similarities in their features without any prior levels, right? So once the data has been collected, the clustering algorithm has been done, then the next step is analyzing the cluster, right? So we analyze the resulting cluster, each cluster corresponding to a pattern or condition with the data, right? For example, normal operation versus an early stage defect or a different kind of loading condition. So that's how we analyze it. So once you have the data, you kind of cluster it or groups together, and then you analyze each of the cluster, right? So once that is being done, then what we do is that the highlight the value. That means this approach allows us to detect the unusual or emerging patterns, right? So once you have the data, from the data as an analyzer or as an engineer, we try to understand, okay, if we don't have a crack, this will look something like that, right? And if we do have a crack, that means it will not look like that. Once you understand that, then you have to understand that what is the intensity of it, and then you have to take a decision that whether the structural behavior needs a full level training data set. That means you need to understand how intense the crack is, and then it's particularly very powerful. I will generally kind of do it mainly for the anomaly detection and early fault diagnosis as well. So that's the basic way of unsupervised learning. First we get the data, we characterize the data, somewhere cluster the data which group it belongs, and from the cluster groups we analyze or try to understand, or compared to the supervised learning. Supervised learning, we already know our x. We say this is our x, and this is our without tag structure look like. This is our with tag structure look like. Now you give me the images which similar to the x, similar to the y, right? Whereas for this one, we don't say anything. We just take the data and then we differentiate the crack and the non-crack data, and then we study the non-crack data, we study the crack data and understand that how that actually possibly looks. That's the basic difference. So in short, you can say that this unsupervised learning actually helps us automatically to uncover the hidden patterns in SHM that will enable the proactive maintenance and better understanding for the structure over the period of the time. So now, if you have a strain gauge data but no labels indicating the damage, so which learning paradigm we generally use? Unsupervised, right? Now let's look into the reinforcement learning. This is also a branch of machine learning that about teaching an agent that how to make sequential decisions. So you will see that it is in between the supervised and unsupervised, but it's having more advantages compared to the unsupervised. So unlike supervised learning where we provide the levels, here the agent learns by interacting with the environment and receiving the feedback in form of rewards or penalties. So what you see in the reinforcement learning is that the agent goal is to maximize the cumulative rewards over time. Okay, it repeatedly takes action, observes the outcome, and then go back and then adjust its strategy. This is very similar to how humans or animals learn by trial and error method, and that's how generally it works. So now if you will try to look into this particular diagram here, here we have the agent, okay, the learner or the decision maker, for example a robot, a self-driving car, a software program, right? And then we have the environment. So the world or the system the agent interacts with. For instance, the road network or a game environment or the process is being controlled, right? And then there is a state of S. There has been action taken as A. There is a reward R. So when the agent is interacting with the environment, the information the agent is preserving at any event of time, this represents the current situation that we are calling as state, right? And then the choices available to the agent at each state, based on the state it selects an action, right? And then the feedback is signal, that means the positive or negative. So when the agent is interacting with the environment, right, the information of the agent preserves at any given point of time, then it's taking the action, and from that it's taking the action, and then from that it is getting the reward. That means it can be positive, it can be negative, from the environment indicating how good or bad the action was, right? So here you can also look into that the agent observes the state, takes an action, and environment then gives a reward and a new state. That means the cycle again repeats. This is also basically a trial and error method. The key to this reinforcement learning is the loop, basically, this particular case. So the agent keeps interacting with the environment. They try to take actions, learn from the environment through reward or penalty to improve the decision for the future. Over the time, it's figure out the best strategy. Over the time, it's figure out the best policy for achieving its goal. And that's how generally reinforcement learning works. So definitely there are, for the reinforcement learning, there are basic builds or the blocks of that, which is the agent, environment, state, action, reward. So they are the main 5 cases. And if you will look into that, first let's try to talk about, so there are few terms also. We need to little bit know about the key components of the reinforcement learning. The first one is the policy. And so this is basically the strategy the agent follows to decide which action to take in each state, okay? And if you can think about the brain or decision rule of the agent, something like that. And then there is a value of function which always be defined by V. This is the prediction, the long-term cumulative reward from being a certain state. Okay, so now let's go back to this particular image and try to keep this image in your mind, and then think about all of this particular policy, value function, and Q value. So policy, as I said, that this is the strategy the agent follows, right? Value is the predicts the long-term cumulative reward, whereas Q value is that you extend the idea of the value function to some specific action. Okay. So now, if you will try to look into the mathematical foundation, generally reinforced learning use, one is the Markov decision process, which is MDP, is quite famous. So basically, what happens here is the very formal framework behind this reinforcement learning case. It assumes that the Markov property, meaning the future depends only on the current state, okay, not the past. So basically, the Markov decision process includes the states, action, transition possibilities, rewards, and the discount factor that prioritize near-term versus the long-term rewards. Okay. So there are also another one, which is the policy evaluation. That's also a mathematical foundation, which is RLUs. This is also a process of estimating how good the policy is. So in other words, finding the value of each of the state or action under the policy. So these components of the mathematical foundation, they form a very strong backbone of how reinforcement learning learns from optimal behavior. Okay. So understanding the policies, the value functions, or the Markov decision process, these are very, very essential before you go and learn about the reinforcement learning, or before you driving into the reinforcement learning algorithm like Q learning, policy gradient. So those are the very, very important factors for you to kind of go ahead and understand. And then there are also several key mathematical foundations of reinforcement learning. As I said, one is the policy improvement, and one is the exploration versus exploitation. Okay. So what is policy improvement? Policy improvement is about refining the agent decision and making the strategy. Okay. So using the estimated value function, the agent will update its policy or choose better actions. That's what generally it means. And that will lead to the higher expected rewards. So when you do that, this is a very critical step when we talk about the iterative reinforcement learning algorithms, such as policy iteration, where the evaluation, those things actually matter. The very, very important one is the exploration and exploitation. This is one of the most important concepts of the reinforcement learning. So what is exploration? That is basically trying out new action to gather information and to discover the potential better reward rather than getting the penalty. Whereas exploitation is that leveraging what has already been learned and maximize its current reward. That's the two difference. Exploration is that trying out new actions to gather that how you can get better reward, whereas exploitation is that whatever information you are having, you are exploiting that information to get better performance or better reward, right? So if the agent only exploits, it might miss better options, isn't it? And if it only explores, it will also waste time and never do any convergence study or never converge it. So reinforcement learning includes strategies like softmax or upper confidence bound to manage this trade-off. So that means these two ideas are very, very important, and all the reinforcement learning must do the both rather than just doing the one. That means refining the policy, balancing the exploration and exploitation, those two together, they are the heart of how reinforcement learning works, okay? And how the reinforcement learning actually evolve with the random behavior to the optimal decision making, right? So again, if you will try to look into the similar case study here, you can see that using this reinforcement learning, we try to create intelligent data-driven maintenance. So first now, if you try to, similar way, try to look into that, let's try to imagine any kind of civil infrastructure. We have the physical infrastructure, right? You can take bridge, tunnel, whatever you want, which is instrumented with sensor. This sensor will continuously send the structural data like vibration, then take strain, displacement, whatever works for you, okay? And once you have the civil infrastructure, then you will learn it from environment, right? So let's take environment as a digital twin here. So basically the sensor data feeds into the digital twin, which is a virtual representation of the physical system or the physical infrastructure. That means this will act as an reinforcement learning environment where we can simulate, predict the structural behavior under different kind of scenarios like different kind of loading condition. So once you structure is there, you have the environment. What do we do next? You have the sensor, right? And then you have the digital twin, which is your environment, which is a virtual representation. So what is the next thing we do here? Yeah. How do we do that? So if you go back here again, and yes, so go back here again, you know your environment, right, from where it is being learned. So what is the important factor now? Agent which is going to learn, right? So your reinforcement learning agent, that means the agent that sits at the center taking information about the structural health and making decisions or action or optimize the performance, reduce the risk. Those are the actions you need. And then once you have that, what is the next one we do?
Depending upon that action, it will be either positive or negative.
Yeah, the maintenance strategy, right? And how does we do it? Based on the agent decision. Yes, based on the agent decision and the observed structural health and optimized maintenance strategies being, for example, scheduling the inspection or those kind of things. Those are the things we generally do. So basically this reinforcement learning agent use the structural health data derived from the environment to improve its policy. So it balances the exploration, that means trying new maintenance strategies. It's also use the exploitation, that means using what has been learned, what works best. So both of the things that actually needs to be balanced, right? So over the time, the system converges on the most efficient maintenance approach. This framework integrates the sensor data, digital twin, and reinforcement learning to create the self-improving predictive maintenance. So digital twin is one of the very, very good example of the reinforcement learning and the whole way that it actually works out. If you kind of think on that perspective, you can think that how actually the reinforcement learning and digital twin is actually connected with each other, okay?
How would you know whether it is good or bad data? Because you have to go to the reward part, it has to relearn how to relearn
Yes.
until we give it.
So you get two types. One is that you have to converge the data, right? Until and unless you are converging, that means you either get reward or get penalty. So if you get penalty, that means what you do is that you go back and you train the data again using the sensor.
This is agree 100%, but how do I know that it is a penalty? It has to go for this
That
penalty.
no, so that's the reason. It's not only the unlabeled data. So you have a prior knowledge that okay, fine. If you kind of have some crack, how it could possibly look like in your digital twin model. So it's not like the whole unsupervised model. This thing that you kind of do not give any data. So the basic difference between supervised, unsupervised, and reinforcement learning is that supervised is you know X, you know Y, you say okay, fine, I want something like that. In unsupervised, you say you don't know X, you give X, you don't know Y, you just cluster things together, right? What is the reinforcement learning is that you have an agent, like maybe take it like the sensor data or whoever it is, right? And then let's say digital twin, right, which will represent something like that. So every time what happen will that if you look into this particular thing, your sensor will kind of continuously take the data and feed into the environment, and then once the environment will be done, then it will using this reinforcement agent, they will understand the structural health. And when we say the structural health, that means obviously you will be feeding some kind of information there. It's not going to be like always unsupervised learning where you don't give any information there. So basically you will say that okay fine, the crack looks like this, Now you tell me that how we can make it better, that it could possibly represent something like that, where you could actually generate it, okay, whatever happening here, you can actually get a perfect convergence model.
So for example, if you take the random persistent information of any of the bits,
Mhm.
we give that value to that changes so that it actually gets okay to check the information on trying to understand
Yes, yes.
then it runs.
Yeah, basically if you think about this speech data, right, so that's where your reinforcement learning will work, that how perfectly it is actually being able through the sensor, right, how perfectly you are making your digital twin model so that whatever happening here, you can actually kind of get the structural health there, and that's the process of reinforcement learning, and that process will take time with the trial and error process. The unless and until you are getting a convergence which is kind of, and once you get a very good award, then it is going to give you the reward from this side, okay, and that's actually going to tell you the maintenance strategy. So basically it's about converging these two through the sensor data by developing this reinforcement learning agent. So this agent is going to learn from this, okay, and then this one is going to give you the data. So basically, and that is going to tell you that what is the structural data, and then you go back again, you feed into the structural data, right, and then you come back and then take the action. So this is going to be a continuous process, because if you will see in real life, it is never gonna possible that you converge it 100%. Especially when we talk about the civil structure. So it's always going to be a trial and error process, and it's also like a little bit complicated compared to the supervised or unsupervised learning. You will never get something like yes or no. So that's the reason you need to have a very generic, or your learning agent and your environment needs to be really kind of choosing that is really kind of important. But yeah, absolutely, it's complicated compared to the other two if you will look into that.
And another thing,
Yes.
supervised learning can be also be images directly
For
without any safety.
yeah, absolutely. So basically, if you think about this dog and cat case, it's the same, right? You put some kind of images. It can be like you put all the images of a breach, okay, from different cells. So it will actually differentiate depending on the quality of it. This is having some kind of crack. This doesn't have it. So if you will look into the kind of more examples of the famous examples, most of this unsupervised learning are being used as an image one, like clustering one. So it could definitely. So basically, it's just differentiating the not similar data together.
The way is without using CNNs. Because if we have to compare the images, or if the program has to understand the image that there is a dog or cat.
So no, the program will not understand that whether it's a dog or cat. Program will do that. These two looks different. They will separate.
Which means image processing has to be carried by the program.
Yes. So basically, you will give the images, right, and they will separate that for the breach cases. Right? They will separate that if there is some crack. They will separate that one. Basically, we don't use it more for the cracks. We do use it for the micro CT scan, microstructures, where in the structure, there are some kind of cracks in the microstructure for composites or metals. It will so it will not say that okay, this is having some crack, this does not have crack. This will just separate those two together differently. That's generally the clustering does for the unsupervised learning. So it will not give you information, okay, fine, this is because you have not put any information. So it is also not going to give you that this is the crack information. This will just separate the data. But the best option is that it can also kind of calculate or identify the noises compared to the supervised learning, especially if you use the DB scan. So for the image also it will be same. It will just differentiate two images where there is some crack, some kind of some kind of anomalies are there. But it will not tell you that okay fine, this is the crack intensity or this is damage. Similar way, if you kind of try to understand the crack intensity, you can actually remodel your clustering model such a way that it will differentiate that which is having more crack and which does not, or maybe have less crack. That's how it's going to kind of cluster the model rather than being very very specific, or because you're not putting the level data also. So that's generally the unsupervised learning. But what I will tell you is that definitely those are very very easy and very easy to understand how does it work if you compare it. Whereas if you look into the reinforcement learning, it's always really complicated to understand whether you come into the correct decision. So I will say that try to see some of the cases that except the digital twin. Yesterday we have talked about 8 different cases, right? So if you can go back and try to think about that where it actually falls about, and you can actually kind of try to solve some of this, it will be really good. We will also see some of the other cases today as well. So now if you are provided with 500 images of the breaches decks, like which is labeled as cracked or non-cracked. So which machine learning approach would be the best to classify nuance in bridge image? Supervised, right? So now I think I have given you the example of how supervised learning level outcome is. So there are few tasks which I have given and how it works and the algorithm examples. Now if you think about the damage state classification, right? So what we generally do is that we train on the vibrational strain features, right? And then we level as a healthy or we level as a minor damage or major damage, right? That's the we do. And generally the models we use are random forest, SVM, visual network. Those are the one we generally use. Similar way, when we talk about the concrete strain prediction, we generally do is that we predict the compressive strain from the mixed properties and curing time and sensor readings, and then we generally kind of feed the details. And the examples or the models we generally use is the regression trees, gradient based, linear, elastic. So very easy, straightforward one. Similar way, the remaining life of the bridge estimation also. So how we do that? We use the historical inspection plus with the load data level with the actual service life, right? And that we kind of feed into the model. And generally the algorithm we generally use for is that the regression with sensor data or survival analysis. So these are the algorithms we generally kind of use. Whereas when we do not give any data or where there is no levels of data, so that's the period when we use the unsupervised learning, right? So now if you kind of think about the unsupervised learning, so the clustering or sensor pattern, let's think about that, right? So how we do that? We group the similar vibration data, or we group the similar strain data, right? Signatures to discover what is normal and what is the emerging region. And then depending on whether all the samples are look similar or they don't look similar or they have different kind of density in the sample or there is noise, we can select this, isn't it? So what is the period when you use the Gaussian mixture? When is the time when, so k-means and d-means can be understood, right? So when is the time when you use the Gaussian mixture? Gaussian mixture means there will be distribution which is Gaussian, right? Then why, when do we use that? Anybody? So if you have some random samples, right, can we use k-means? Let's think that all look similar, all the data look similar, right? But the sampling techniques or the way we have selected the data is very random. Then can we use k-means? Sorry?
It will generate hard clustering. Like k means we are only using k value as 3 or 5, but with random distributions it will convert the clustering into very hard process or complex further. With using Gaussian mixtures, we can randomly distribute the unknown parameters while using Gaussian distribution or any other model in Gaussian mixture.
So you say that for k-mean we cannot do that because of the computational efficiency. But what if that we kind of take a very small numbers and it's random? Can we do that using k-means?
The computation
But basically, if they are randomly distributed, there won't be like any cluster. That's how it's very difficult.
But what if that they are a little bit similar to each other? There will be data which will be similar to each other, right? And there will be data which may not be similar to each other. Can we use k-means?
If they are similar,
We can. But one of the rule of the k-means is that the clustering has to be very kind of close one, isn't it? So I will say that go and try to look into this 3 different ones and try to understand how it could possibly work out, okay? And when you have some kind of random samplings, maybe it could look similar, right? Or maybe it's not looking similar. It may we're not talking about noise anymore. So let's not talk about the dB scan, because some way it's gonna work out if it does. So try to understand that when you have some kind of random samples, what happens if your samples are not close to each other, or how about that your samples have some grouping but it's close to each other. Okay. So try to understand that how these three possible cases could possibly look like if you group them for any such. But what you have to remember is that we can group all of this. Okay. It only depends on the types of sample and the quality of the sample, like what is the what is the type of samples you are taking into. But all of these three we can group for different three varieties of cases. Okay. So try to have a look into that and try to understand that how we can get the normal values. And then exactly the another one is the anomaly detection for the structural health monitoring. So we can model the healthy features of the structure as a potential damage. Also we can do that. And there are several processes like the forest auto render. So there are different ways we could actually do that. And then the another one is this so the main important one is the first one. That's why I'm saying that please go back and try to look into that how it is different than each other. Okay. Because I think tomorrow at the second half we are going to do a little bit of tutorials. It's very, very important that you understand most of this, especially the important one in supervised, unsupervised and reinforced. Okay. And then dimension reduction of sensor network. That's also something I think we do quite a lot in SHM, because we know that in SHM the number of samples, yes, are very, very, very one of the very strongest or one of the very biggest issue. So what we do is that we compare the hundreds of sensors to few principal components to visualize the cluster analysis. So there are several ways of doing that. Several research have actually been done that how can you reduce the number of samples, and that can actually be done manually without using any unsupervised learning. Okay, if you have a small structure. Or what if you don't have a small structure? You have a big structure where you need to attach lot of PZTs or any kind of sensors you kind of think about. Then there are several ways like PCA. There are a lot of like QMAP. These are not quite good enough, because definitely at the end of the day you will not get the exact result by using the more number of sensors. But still, there are people are actually working on PCA, UMP to kind of understand it, to kind of reduce the number of sensors. Some may help your cost efficiency, some may help your labor cost. So many things actually get affected into that. There are a lot of studies that are actually happening in this area. But I will say highly the first option, the clustering of sensors, very, very important. So please try to understand the difference between KME, DB scan and clustering and Gaussian mixture, and try to think about your samples can be random. Yet may have some relationship with each other. It's not as random that they are so scattered. Okay.
How autoencoders beneficial in the anomaly?
Sorry?
How autoencoders beneficial in the anomaly detection? Do we go to the transformer like that?
When you think about this auto anomaly, the auto encoder is basically you that will actually giving you some information about the potential damage. So it's also like, as I said, that the anomaly detection is some way when we talk about the structural health. So I have not used much into the auto encoder, but it's mainly kind of giving you the information that whether there is some potential damage or not, and that's also similar way. But when you talk about unsupervised learning, for the SHM especially, the clustering is the main thing, or the main approach which we do. And if you think about the dimension reduction, that some way comes under that clustering, or the auto render, that's or the isolation forest. So this will actually kind of separate the data some way. So all of this will some way follow that, giving you the separate kind of value. So if I could actually draw something, then I could actually show you that that basically you get the sets of data which does not look same with each other, and they are
That's why autoencoder work on the encoding. First we encode the data.
For auto encoder also you give some information, but you don't say that your y how you give the value of x, but you do not say how your y will look like.
But in X also we in X the input data we do some type of coding like embeddings. Embeddings. Like autoencoder works like on embedding. But later how we once we encode, then later how we decode because there is no transformers. Then how we
that's the way that you have to understand using the autoencoder, right? Basically, you may give the information X in such a way that there may be some relevant information of Y, right? But when you get
get the autoencoder value, then you have to understand that how it could possibly. So all of this, for even for the k-means and all of this, you have to analyze the data. It's not going to be like as similar as the this one, right, or the random forest and all. So for all of this process, there is a learning, or there is a differentiating the data, that how it could possibly give you the exact result. So for all of this, it's not going to be like giving you the exact y. So all the y you have to analyze to understand that how the y is going to be, relevant with you, or the information which you are looking into, how relevant it will be. But for every of this case, you are never going to get the very straightforward y. You have to have some knowledge, and the knowledge can be that you kind of code that to get again to get your data, right? Or you can analyze the data again.
My question is
Yeah.
quite simple that if we import something, then there is some also decoder process.
Yeah.
But here you only encoder, not the decoder. And when we combine both of encoder and decoder,
That
then
depends on.
become the transformers.
No, when we talk about the unsupervised learning, we are not using the decoder here. Okay, we are only talking about the encoder here.
We just import the input data.
Yeah. No. So when we use the auto encoder here, that means that we are giving the information of the structures, right? And then once you give the information of the structure, you get the details of that whatever information you get, you give it like something like healthy feature space, something like that. Let's say that it's healthy, okay? So from that you will be actually analyzing it rather than you kind of decode it. And some way you will say that that's also like decoding the analysis, but you are not using it together, if it makes sense. So your question is that if you are using the auto encoder, we are also decoding the result. That's what, right? But that we are doing for all of the cases, isn't it?
Transformer works like that.
Transformer some may work like that, but then some way you also need to give in some information there as well when we talk about the value of y, don't you?
Transformer to not calculate the value of y. There is no need in the transformer. There is no need of output.
No, but if you look into all these values, whenever you give the value of x and you get some kind of result, you do actually kind of analyze that, isn't it? And that's why some way also calling the decoding or analyzing the results. So that's going to be happen every case of unsupervised learning. You cannot actually do that without analyzing or whatever you can say that decoding the results. You cannot do that because you don't get any straightforward y value, isn't it?
Ma'am, the initial input is something like suppose in terms of image, and
That's also
input
depends.
all image in some digital, suppose in digital terms like some numerical values. But when the output came, that will be numerical value, not the image.
No.
Then how we recognize?
No. When you give the image, right, you get the values as an image. So basically what you do is that you give the image, okay, you say that, okay, fine, this is the images, and in the images, when you get the results as an output, right, so you will definitely get as a value of images, right?
But the autoencoder is not
Yeah, that's the reason you say that, okay, fine, it is the healthy, the stiffness value will be like that. So the stiffness value will lie from this to this. And then you get the value of stiffness for any kind of structures or the damping matrix, mass matrix, the value of this. That's the value you will be getting from that. You can decode and understand that, okay, fine, if the stiffness value lies under that, if your mass matrix looks like that, that means that it's a healthy structure, and that means it's not a healthy structure. So it's not necessary that for this one we need to give an image one. For the image one is basically works for the first one, not the second one. Does it clear your this thing? Okay. So whatever information you will be giving as an X, you will someday getting similar information as Y. Okay. So when we say the structure is healthy, structure does not have time, does not always mean that we have to give the image. There are other structural properties we can always give, and from that we can calculate whether the structure is healthy or not healthy. And that is like can be mass matrix, stiffness matrix, and those things. Yeah. No. So there are separate manual processes how we do that. If you think about a structure, right? So somewhere in the manual way, what we try to do is that we identify where there would be more number injection. We put the sensor somewhere there, right? And that way we reduce the number of sensors. Yeah. So absolutely. That's what generally usually happens. So if you have a small rectangular plate, you imagine, right? So you have like two holes, and that we say as a damage, right? So we try to calculate at which place, if we put the sensor, we get the maximum damage details, right? Yes, yes. Similar way, if you think about a large structure. So there's a large structure, manually it's very, very difficult to do that, right? So that's the way then, we use this kind of methods to understand where you kind of put the sensors, which will give you the maximum better result. And that way, yes. So we are trying to reduce the sensor, but then we are also trying to get the better performance. And then definitely, as I said, the reinforcement learning. So that's something is also, as I said, compared to the other two, it's always a little bit complicated. The first one is active structure and control. So basically, our reinforcement learning agent that tunes active damper or tunes mass system in a real time to minimize the vibration. Right? This is actually can happen using a lot of examples like Q learning, and you will see that these are not quite advanced compared to the first one or the second one. So these are still kind of a lot of research are still happening. So you may also see that the most of this algorithm you may have heard and may not have heard about, because these are still very new process. And another one is the inspection of the scheduling. So the reinforcement learning also decides when and where to send the drones, right? Or inspection to minimize the cost while keeping the risk low. So basically then there are like policy gradient, multi-armed, those are the things which actually mainly work. And maintenance and retrofit planning that when it could possibly happen. Sequentially choose the repair action to maximize the infrastructure life cycle performance, and that budget crunching. Definitely budget is also something, when you need to do that, why you need to. So those are the things actually you learn from this. And the methods we generally use is the Monte Carlo research or the model based one. So the main three, if you will look into these three main differences here, the supervised, unsupervised, and the reinforcement learning. You will see that in supervised learning, what we predict or classify a known target, right? And what do we do in the unsupervised learning? We try to reveal the hidden feature, hidden structure anomalies. And how about the reinforcement learning? If you try to look into these three particular cases, okay, what do we do in the first one? We think about all of this together and try to say one, summarize in one word. What we do here? Yeah. Predict or classify the known target. And how about this one?
Outliers.
Sorry?
Cluster or outliers.
We're doing clustering. Let's follow clustering. What else we do? If you think about the prediction in that way, what do we do here? And what do we do on the reinforcement one? So if you try to think about this one, in one or in maybe 2-3 words, how will you define the whole process? Try to understand the hidden data or some way reveal the hidden structure or anomalies, isn't it? And how about this one? Yes, and then what to do next? No, I mean the reinforcement learning we do, because we try to learn from the environment and then take the decision that what is to be done after that. That means that can be maintenance, that can be retrofitting, that can be inspection scheduling. So basically we learn from the environment that what is being needed and take the action accordingly, right? That's the main key difference between that. Yeah. That's the reason we are saying that we are revealing the hidden anomalies. That's the reason we are saying that we are revealing the hidden structure, because we don't know about it, right? So clustering, anyway, we are doing it in unsupervised learning, right? That's not the main goal for us. That's the process we follow. Like linear regression, we do follow a process, right? But what we want to achieve, or what we generally get from it, we try to kind of get those hidden anomalies. We try to understand the hidden, structures or something like that. Basically, revealing the hidden anomalies, revealing the hidden structures from this. And reinforcement, as we said, I think what you have correctly said, that we kind of learn from environment, learn from the policy to kind of take action, what to do after that. That could be anything. That could be taking structural control, taking care of the maintenance, retrofit that, or inspection. So those are the things, anything, depending on the environment. As an agent, you understand what works well, and then you take the decision. Okay. So again, I think this quizzes are very, very simple for you all. So an innovative model learns over the time which maintenance action, that is inspect, repair or innovate, yields the best long-term structural health outcomes. So receiving rewards or good decisions. So what type of learning is this? Reinforcement learning, right? So now, before actually going into the next one, do you all remember that yesterday we have talked about 8 future trends of the AI, AI for the sustainability infrastructure? So now can you think about the supervised, unsupervised and reinforced learning, these 3 cases, and can you try to connect with one of those? Let's first talk about the supervised learning. Let me just yeah, so let me tell you all this again. The first one was the integration with IoT and IoT-enabled sensor. Then one is the drone and autonomous inspection technology. Third is the advanced sensor technology and fiber optics. And then the real-time monitoring and early warning system. Then role of digital twin. Then definitely the blockchain and analytics. And you have the 5G cellular network. And the last one is the large-scale SAGM and AI-driven maintenance. Okay? You have 8 of this. Can you try to at least relate one of this with the supervised, unsupervised as well as enforcement learning? So we understood that digital twin connects a lot with the reinforcement learning. So let's not take that one and try to get something else if you get it. But it also depends on how you are feeding the things, right? Maybe you get the sensor data from the drones, but if you don't say that, okay, this is not a details of this, you get the images, but it can also be unsupervised, isn't it? Yeah, depending on how you are defining. Anyone else? Sorry, I couldn't hear you. Reinforcement or? Why?
Because we are taking data from AI, so the AI will learn from environment, and if we define the input and output, the target would be unlabeled data. We have to find the hidden anomalies, or in reinforcement learning, the agent, the
Learn
AI.
from the environment, yes. Yeah, that's a good example. Anyone else?
And blockchain will come under supervised
Which one?
AI and blockchain, because blockchain will decentralize the data, and it
And
would
you need to identify that what the security lines and all those details are. So it will definitely come under supervised learning, right? Perfect. Anyone else?
The early warning systems shall also come under the reinforcement learning, and is it in past or sequential learning and decision making. So
Yes, absolutely right. Because you learn about from the environment, you kind of fit in the details and then give this. Anybody else? about the other ones like the 5G network and the other details?
Some optical fibers one will come under supervised learning because the data they carry with them are signals, and signals are mostly labeled for the hub or the broadcast to identify for which IP address or which sensor it should be sent or how it is
Yeah,
connected.
but for the fiber optics, it may not be always important that you tell, okay, and this is how damage it would look like, or if there is some kind of acoustic emission, you may not identify. Definitely, there are the IP addresses and those things will be there, but the nature of the data, it's not always necessary that we give the information that is the correct data
Yeah, it would come under unsupervised
or supervised. Yes. It can also come under enforcement learning, isn't it? That if you kind of use it as a sensor and learn it from the environment and give the details to the agent, then it could also become under enforcement learning depending on how you are defining your X, right? And Y as well. Okay, so I will say that try to go back and think about it. But most of the cases you will see that it does not fall actually under one. It actually kind of can be mixing of supervised or unsupervised or actually reinforcement learning, depending on that how you are defining your data, or some way how you are kind of defining your X and Y. So that's the main way we generally kind of do that. And I will say that go and have a kind of look into that. So now I will kind of give you one of the few of the future go back and try to look into this study, and I have tried to give you one for the supervised learning and one for the reinforcement learning, because the unsupervised learning is some way going to be some way similar on the line of supervised learning. Only the difference is that you are not leveling the data here compared to the supervised learning. So the first one is, as I said, that try to imagine that you're tasked with the classifying healthy versus damaged. Let's talk about the sensor here. So what kind of features would you extract, like vibration, temperature and all, and how would you handle the imbalanced data if the damage cases are there? And then which performance matrix would you trust most and why? So I have imagined that most of you are coming from civil backgrounds. That's the kind of way I have tried to set up the question. But if you are not comfortable with the breath sensor, you can actually consider for any other sensor as well. Okay, for any kind of another civil infrastructure or any kind of infrastructure, right? So once you kind of have the model, your model is ready, then how will you predict the damage that with 95 or very close accuracy, but misclarifies how the true damage cases? And what does this simplify about your data or the model? And then again, how are you gonna fix it? Right? Think about the whole perspective and keep in mind that when you are making this model, you are defining what is damage. You are defining what is damage. So basically you are giving your X, you are giving your Y output, and try to think about how this possibly could look like, and what if that you don't get the accuracy, how will you go back and try to change it? You may not take the big sensor, you can take any sensor you want, you can take any infrastructure you want, and try to kind of make a model or build a model and think about it. And trust me, this is going to help you tomorrow to understand the tutorial. Okay? Similar way for the reinforcement learning also, I will say that look into that. If you are designing a reinforcement learning agent to schedule any kind of inspection, how would you design that the reward balances the cost and the risk? That's very, very important. And what happens if your rewards is heavily penalizes inspection but lightly penalizes failure? And then once you have your reinforcement learning policy, which starts inspecting more frequently than human engineers typically do, what factors could cause it? And how might you consider, or how might you constrain or guide the agent to keep it more realistic rather than becoming more fancy? Like you may have like a lot of data, but how will you kind of make it more realistic or real life? So these are the few questions. I think it's very important for you to go and have a thought about that. If you kind of imagine or make a RL model, then how it could possibly look like. Okay. And before I forget, so I will suggest all of you, if you can bring your laptop tomorrow, and you can use any software, you can use Python, you can use MATLAB, but it's very, very important if you can actually have one of those softwares in your laptop. So tomorrow it will be help us to kind of understand how one of these could possibly look like. And then as I said that, so basically in today what we have seen the three main core paradigm. One is the supervised learning, that's the classification, regression. Then the unsupervised learning where we see the clustering or PCA, that means finding the hidden patterns, reducing the dimensions, and then reinforcement learning. That means we are training the data, so training the agent to make the subsequent decision. That means what needs to be done and how we get it to maximize the rewards over the time using the trial and error method. Okay, and then definitely data is a very very important factor. That's the foundation of all of this monitoring. So how we can collect it, that can vary depending on the sensor you use. I think you can be sensor based, you can be cloud based, you can have previous data from the history data. So those kind of different way, but we need the data to kind of do this. And then as I said, the dimension reduction or feature extraction is something very very important. And how you are applying all of this in the application of SHM. So that's also something very very important, that we are using for anomaly detection or we are using for damage detection, load classification. Those are the applications we have actually seen, and basically understanding that how combining the AI inspired machine learning algorithm with robust data collection. So we have seen that what if your data is robust, what is it does not have same density or does not kind of look similar, then how we could actually do that? How we do this using unsupervised learning, right? Or if you have the known data, then you know your X and Y, then definitely using the supervised learning. Or you want to learn from the environment, take the decision, then we use the third one, right? So basically combining all of this, we have kind of tried to understand once you have robust data, with the collection enhanced, how the sustainable infrastructure monitoring happens, and that is kind of going to help you to faster insights and better decisions, and making your infrastructure monitoring more sustainable. That's the kind of a summary of the first one what we have seen today. And as I have always kind of told you that these are the all references which we have followed in the lecture, and these are the few of the references which may have not been followed, but it can be useful. So I think especially the last one is a very good paper to understand the reinforcement learning. So if you are interested about how it could work, or the second one where they are talking about the whole aspects, and it's a very good review paper where they are talking about the whole aspects of machine learning, and they are talking about basically the practical decision making or the application. Though it will see that we are talking more about the very broad engineering perspective, but I think it's a very good idea to have a look into that. Similar way, the first one also, they are also that is also like a review paper where they are talking about the supervised, unsupervised, and reinforcement learning. But again, as I said, that's very much as a broad engineering aspect rather than just using on civil. So I will say this is, if something you're interested, you can definitely go and have a look into that. And so now today we will end the lecture here, and I think I will see you again around 3. Yeah, thank you everyone.
One online participants wants to see a slide which have classified how supervised and unsupervised learning.
Sorry?
One online.
Yeah, just take
A slide which have I guess classified how supervised and unsupervised learning.
साउंड करेंगे आप इधर क्वेश्चन करेंगे पार्टिसिपेंट
Yes, online.
Yeah, I think
पूछिए
can you
बोलिए
hear me? I can actually okay, so I think that slide was not shared with him because there's only one here. So I can maybe I can show it to you all also. So I think yesterday I had showed a slide where, but I can show it again to her.
Yes, you can.
Yeah. Let me just share the slide.
चैट लिख दीजिए पूछ सकते हैं क्वेश्चन सुनाई देगा
Yeah, so I have shared the slide where all this details are there of this. I think you guys have already seen this. What is it?
It is visible.
Yeah, I'm just trying to show you all as well. I think you can see right now. So this is basically the all machine learning algorithms which I actually showed you yesterday, if you remember that. And the most of the machine learning models which we are going to talk about It will all fall under this umbrella, and mainly the all main 28 types of machine learning algorithms which we generally see. We are going to talk about most of this in the lecture, and then there will be some we definitely not going to talk about this lecture as well. But these are the main foundations of the one, which is the classification, optimization, migration, clustering. So all of this actually comes together. So I think Anand Babu. So yes, Anand, can you see it now? Or do you have any other doubts? I'm not sure if he can hear us.
He wants to ask, can we use data?
Yeah, definitely. Data fusion is one of the very common practices which involves combining the multiple resources to create more complete, accurate, and insightful representation. So if you think about the real life applications, yeah, definitely we can do that, and that will actually help us to reduce the uncertainty and reveal the new patterns as well. So we can do that for individual data sets as well. And there are several ways we can do that, like aligning and processing is one of the very useful one. I think we do use it quite a lot. Basically, how it is useful is that it helps us to reduce the uncertainty. It also helps us to understanding the insight, cost effectiveness. Those are the improving the accuracy. So you will see that this is the way we can do that, and how we do that, like sensor fusion, cloud data fusion. And then there is a multi-model data fusion as well. So there's a different way we could actually do that. Yes, absolutely, Anand, we can do that. Yes, we need to make a hybrid model. Actually, I have worked on this. If you are interested, I can share some of my paper with you. We can do that, and that will help you to get better performance if your one machine learning model is not capable of giving you, the expected output. Yeah, okay, thank you, Anand. So anyone has any further questions? If not, then we will end the session. Anyone has any further questions? If no, then thank you everyone. I think I will see you all in the lecture 2 today. Thank you. Bye-bye.